So here we go, hello A48, and here we go. This is the assembly file. So I was thinking, okay, that's cool, let's work on the G7000, and we can use command line, right? So Windows. Usually I don't have this low resolution, but it's much easier to show you. So now I can write ASW. So I get ASW. And that's an assembler, and the W is for Windows. You can get ASL also, which is for Linux. I was wondering about that because in the documentation for this G7000 RAM, it was using ASL, not ASW, so you can see many processors. So what I've done, if you write path, you can see that I've put, I put C colon ASW cur.bin or -bin. I can show you. ASW cur.bin. There you can see the executables. We also have P2 bin, which is very important. So we'll get to that also. So you can assemble here manually, but what I wanted to do is to use the run function. Just press F5 in Notepad++. So that's much easier. So yeah, this is the second take I do for this video because I was. So you can recognize if it's SH script or div ASM, whatever it is. So you can jump in here. So actually, when I come to think of it, if this assembly doesn't work, I should say error level and then go to. I don't remember exactly how this works, but go to the end. So if I do the end here, I think it will jump there if something goes wrong. So yeah, so let's keep that. So now if I do run, I can then launch this script with a couple of parameters, which is current directory. Let's see what that is. Actually, I have a full path of the file now, so let's run it. Oops, it didn't work. The reason for it doesn't work is because you can't assemble this script. So, but that's the thing. If I now go to this assembly file and press F5 again and then run, you can see it assembles. So that's really cool. So now we have the possibility to assemble from scratch. So this is an example which comes with the G7000 RAM. I made a board for that, and we will hook up my new logic analyzer. I have a 24-channel logic analyzer. It's called Digital Discovery, I think. Yeah, and you can see in the script is assembles hello.a48. I don't remember exactly what that was. The CPU is 8048, and then include whatever is in ... or the source directory, which is in the parent directory. So I think maybe I have it open here. Source, and there you go. It's the header file. Okay, so the header file I have here though. So basically just a listing of BIOS routines for the Videopac. So these are actually memory addresses inside the ROM, which is in the internal ROM, which again is inside the microcontroller package. It's inside the microcontroller itself. So you have also other registers, not only the ROM. So or the ROM routines. For example, we want to write a chart. I don't know exactly what this means. I've heard that this is to the first char, but I think maybe is this for the next line? Not sure. So yeah, so I think you have audio also in here, audio routines. Here, these are defines for what color you want. So yeah. Anyway, so let's get back to the hello world. Probably copyright, but who cares? It's 1977, isn't it? So you can read all about it. You can see the 8048 has 40 pins. It has a 1K internal memory or ROM, and then 64 bytes of RAM. You can also see, this is the memory as I was talking about. To see the first 7 registers, they are actually located in RAM. You have the same register can be located here if you're in bank 1. So that's also a bit annoyance with this architecture, that whatever you put in R0 doesn't have anything to say if you jump to another bank. What this program does is it just writes hello world on the screen. So you put the first char in R0, X and Y position on R3 and 4, the length of the string into R2, and then a pointer to the string. And this is the pointer address. You can see the address is down here. Hello. This is what the assembler does, right? So, right, you could have written the address of that data which starts there if you just count down. But what if you put in another line here with another machine code? Well, then this address increments. So then you have to change all your references. So that's what the assembler does for you. It keeps index of everything. So yeah, so back to this memory loading thing. You can see that it puts a pointer to this string, which is hello world. You have to trust me on that. And then it puts that one into the accumulator. I don't think there's a picture of it here. Maybe it comes later in this diagram. We can I took a picture of it. It's much easier to just open it like this, right? You can see the accumulator here, which is a very central part. You can also see all the registers there. So this is basically the RAM array. It says that also you have the stack, and then you have an optional second register bank, which is 0 to 7 again, which we talked about. But these two are special, these two first. So the first one points to it's indirect addressing, if you know what it is. So you put the pointer onto A, and then you move P, which means I think you move indirect from memory back into A. So whatever you had on A will now be replaced with the actual character value, which you were pointing to, hello string. So actually you get this value in here. So you can see it's a bit work. But that's very typical. You can see all the location in resident data memory are addressed indirectly using register 0 or register 1 to specify the address location. The special symbol @ commercial @ indicates that the indirect address is desired. So yeah, so these two instructions are not the same because the opcode, operand is different. So this is the opcode. So we can I should read this actually, but if we carry on, get it. This is the DJNS set. It's like decrement, a jump, not 0. So it's like you can loop down to 0 and then jump. So, or it jumps. Yeah, that's what it does. It jumps if it's not 0. So it finishes the loop until 0. That's cool. You can jump if an input called T0 or T1 is high or low. So that's also cool. You can, I think also there's, JBN. You can branch when the accumulator is high or low. So this is bit testing actually, so you can look at that also. Here you can see the at one. So you can see there's only one bit in the operand which you can change, because it's only R0 or R1, because those are the two indirect you can use. You can't say R2 here, doesn't work. So let's bring it back to where it was. Now I wonder, why is it in R1? That must be because this program is located on the external room, right? I haven't thought about that. I thought it was going to say R0 there. But remember, this program is in the external room. Then you move the accumulator, which is now the character, into R5. Remember, we have used 1, 2, 3, and 4, and 0, and now we are using 5. That becomes important for this print char. Just the way you have to set it up for print char to take over, I think. So yeah, so let's assemble this. Run. It's assembled. And if error level 1, then seems to be doing the B2bin anyway. You can see if it actually doesn't do it if I do something like this. If I break it, it seems to do it anyway. Yeah, it doesn't understand go to end. Well, maybe I should remove then this. Let's try it again. Boop. We have an error in the code, and then it says error invalid symbol, and then it checks if the error level is 1, because this assembler returns error level 1. So then we check if error level is 1, then go to end, and so it does. Okay, now we can turn echo off, so the output is more clean. Try again. Yeah, that looks more clean. Now we know that our script is working, so we have an error, so it stops there. So that's great. So we can delete these two, so you can see what comes up. Object file is something that was there from the example, so I won't touch that. Let's run it again, so you can see you get no extra files. Okay, so let's fix our error. Try it again. Run. And there you go. You have the list, and then you have P, which comes from the assembler, and then you have bin, which comes from P again. So what's the point of having this extra P? Well, this P is just it's like not sure what it's for. It's for a programmer, I think. It's like an EEPROM programmer format, I think. So you have the same code in here. It's not encrypted or scrambled in anywhere or translated, except when you make the binary, you get it to start where your code actually starts. So let's see. It starts at 400. Let's go to 400, and there's our code. And what about hello world? Well, you can't see that because it's not ASCII. Down here you have a hello world, right? But what you can see, you have two L's, hello, and then world down there. So at least you can see there's 2L, because you know there's, well, actually you can see the code here. D1D12OE, 1D12OE, and so on. Another thing you can see is the first instruction is jump select game. So let's have a look at that. GC, JF, these are the brands. There you have jump. Okay, so you can see this is a bit difficult because it starts on the other end and then end on the other end. So a jump, to an address, so select game. The problem here is that this binary is larger than 8 bits, therefore they have 2 extra bits there. So let's see what that is. Select, there you are, 2C3. So we can forget 2 for now. Well, we don't have to forget it. We see that this is 4. So it's 2. These are nibbles, right? So this is C3, and then this is 4. And then if you have a 2 there, that must be the bit number 10. So yeah. So I think it's A4, and then C3. Let's see. In our hex, C3. There's C3. So yeah, because 2 becomes 4 because it's shifted to the left. Okay. So let's move on to the next instruction. Move immediate. I call it literate, but anyway, immediate data. So this data is VDC char 0. So let's see what that is. It's 10. Okay, so 0. So it's 1 0 0 0 0. So this one's 8, and this was 10. So 8, and here we have A plus 1 is B. So this is B 8 10. So let's see. Can we find it? B8 10. There you go. So this is where you can go. We can find another one if you want. We have the next one, 20 into R3. So we can see 20, but why is R3 BB? Well, we know that this is B, and 3 is A, and then these two, which is A and then B. Yeah, so it's basically just algebra, or Boolean algebra. And so on, you can go on like this, and then you end up with this hello world string. So that's it, and the rest is just padded with zeros. Finish up the board, but first I need to look at the glue logics. So this is the microprocessor again, so I thought maybe I can simulate it. And then of course I had another idea how to do this. So here you have the read strobe, write strobe, and up here you have the strobe for reading program memory. So there's like an interaction thing going. This port, which is connected to a register, or gets data from the register, has to be set such that you get the correct chip selects. Right, and you can also disable this line by setting this P16 high. Yeah, so I have the simulator here. Let's load up the, sorry for the camera stand here, or arm. I have ordered a USB microphone because I'm tired of recording on the screen at the same time and joining the audio and video together. So let's see, so down here at the bottom you can see read and write, and then these 3 ports, and that basically is these 3 ports. The last one isn't important really, but I have it anyway. This circuit is the same as the RAM card from what's it called again? Yeah, Søren Gust. Keep forgetting it. RAM, ROM. You can notice that the program fetch strobe is connected all the time to the ROM, but it's not used when the RAM has the program. That means that the menu button goes from menu to game. So but it still gets those pulses, but it's disabled with this G. It says G, but that's like a chip select input. So that comes from this gate here. And this is the same I'm trying to simulate here. So, and I have attached something on the edge here. I'll talk about it later. So if I go up here, I can say ticks enabled, So this is like program select enable or whatever it says. So this is like the CPU wants program instructions, and you can see the RAM chip select is pulsed. Now if we are in the menu mode, let's click it, you can see that this pulsing is not coming through anymore. So that's the function of this gates here. So a high on this will always be a high on the output. So let's get into menu mode. So the PS enable is not coming through, so that's great. So what we are doing here is in the menu mode is that we have an external ROM which the program is running on. So it's not shown here, but this line is going directly to the ROM. And you can also see that the ROM enable is enabled. So, and I think maybe that changes. Yeah, you can see it changes when you go from menu mode to game mode. Then the ROM enable is disabled. So that's the function of this gate up here. So, because then we want the RAM to take all the you can see, now we are in game mode. The RAM chip selected pulsing, and the ROM is disabled. So that's working. What I was doing over here, I can see if the thing is, this one is using like 5 gates. That means I need 2 packages, and then one for this one. This one is not there actually. So I need 2 IC packages with 4 gates in one, and another OR gate. So what I sit with is 2 extra of these, which are not used. So I was thinking, okay, if I'm going to use this chip select thing, then I need an inverter. So I need another like gate. So I was thinking, okay, let's change these 2 OR gates or NOR gates. So the way you do that is that you put balls on all sides, sort of, or you can move that ball over here on both inputs. That means it's the same as these having balls on the outputs, like here. So to simulate that it's actually the same thing, let's try it. Let's go into here. Now we can see that the output is pulsing exactly like this one, even though it's OR gates, NOR gates instead. This can also be a NOR gate. So I had an idea that the CPU doesn't need to get the data to write it back to the RAM from the SD card to the so SD card, CPU, and then back to RAM when you are loading a game. But what we can do instead is right, it is using write, but what if you used read? And the reason why I think that is because, let's say we say to the CPU, let's read some data from here, but don't care about it. What happens then is it strobes the read line here. This is from the schematic. So it strobes the read line, and then if we connect that read line to this one as a write instead, then we write to it when the CPU wants to read. So then we know that the CPU doesn't put any data on the bus, so then we know the bus is free. So if the bus is free, then we can put data on it at the same time. So I was thinking maybe we can use the Arduino to put data on it. So what I'm thinking then is this is like my drawing of the schematic. Like this, you have a CPU here, or a microcontroller. You have the associated ports, and then read and write strobe. So I'm simulating it here because it's easier to see what's going on. So yeah, so if I flip the read, you can see what's going on here. He uses WR, but we want to use read instead. So let's see, if we had used VR, then it's this line he connects to.
up here. But if we take this line, then we can take a read instead.